Thank you everybody for coming. Today we will be covering all sorts of topics around continuous monitoring and HUMS based systems. Here's a quick agenda. We're gonna jump back into history and then see how it certainly is affecting what we're doing now. We're going to talk a little bit about maintenance assistance on platform tests, identify what it is, how it works, what is continuous monitoring, how that works, go over a couple, three or four industry examples, talk about the implementation, and then, of course, open it up for questions. So let's bring it all the way back to 1982. If you do a search on Google or Wikipedia, you'll find that it states that one of the first continuous monitoring applications was back in 1982, and it was invented by Carnegie Mellon University in Pittsburgh, Pennsylvania. Talk about Back to the Future. I recall as a kid looking at colleges with my dad, and he wanted me to go to CMU. He wanted me to major in computer science. Well, one of the exciting nuggets from the campus tour was the fact that all the Coke machines were networked to each other and to the general student population. So anytime, anywhere, you could find the coldest Cokes on campus. Yeah, this is credited as the first IoT application for continuous monitoring. And no, unfortunately, I did not attend CMU, much to my father's chagrin. So we certainly have come a long way from monitoring Coke machines. Instead of on-platform testing of the compressor to keep the drinks cold, all of this can be applied to the aerospace industry as well. So we look at three critical areas that on-platform testing can help on an aircraft. And they are, for instance, aircraft systems, looking at malfunctions such as navigation, communications, or sensor areas, looking at the electrical and power distribution systems, looking at faulty wiring, faulty connectors, or power supply disruptions, and then, of course, the hydraulic and actuators, looking at faults, enabling the identification of leaks, pressure loss, or malfunctioning control surfaces. All these you can certainly monitor continuously. So how can you find or diagnose any of these issues? Well, one option is platform test. And here's how we typically think of it. The first thing, of course, is problem detection. Can you identify the issue based on alerts, abnormal behavior, or actually data from a health and usage monitoring system or HUMS system? This could be through automatic system diagnostics or pilot or engineer reports. Typically what you do is you do a walk-up inspection of the aircraft with portable test equipment, such as data acquisition and control devices, and probably perform a visual inspection. You would do a system verification by connecting the tester to the aircraft system and run diagnostic tests to verify and flag the issue. Typically, you could analyze live data and compare it against expected parameters to confirm the fault. Once verified, you could isolate and document the affected system to prevent further issues. Typically, you would document the fault in the test results, detailing the impact on other systems or other subsystems. And then, of course, you would remove it for maintenance if the issue cannot be resolved on platform. Typically, you need to ensure proper documentation as well for traceability and compliance. So testing on platform or on vehicle before reaching the maintenance, repair, and overhaul or the MRO facilities, it provides significant advantages. Traditionally, testing often requires the removal of the line replaceable units or LRUs or other systems, which is both time consuming and costly. However, with the advent of portable, rugged, and flexible test systems, this is no longer necessary. Portable test systems now allow for on-platform, on-site testing, eliminating the need to remove systems from the aircraft. This not only saves time, but also reduces the risk of damage during removal and reinstallation. By testing systems directly on the flight line, labor and resources required to remove and transport equipment for testing are eliminated, and maintenance can be performed more quickly, resulting in better overall efficiency. And then, of course, on-platform testing with portable systems allow for quicker turnaround times. This is particularly important for commercial airlines where downtime directly impacts revenue and, of course, your frequent flyers. Portable test systems are highly flexible, allowing them to be used on a wide range of aircraft and systems. This versatility makes them a valuable tool for both the MRO facilities and flight line operations. So all of this helps for immediate identification and diagnosis of the system issues. It helps minimize system downtime and, of course, ensures timely maintenance decisions. On-platform testing requires acquisition and control signals at the right places with the right sensors. If it is on platform continuously for health and usage monitoring systems, the size, weight, and power or swap requirements become more important than a portable test rig to co-locate to the platform. They may be the same or similar signals, making the requirements for similar hardware critical for code and system architecture reuse. Ensure that your hardware selection allows for this. We have mentioned continuous on-platform monitoring, so let's define it. Continuous monitoring refers to the ongoing real-time collection and analysis of data from systems, machines, or environments. In the context of aerospace or other industries, this involves the use of sensors and data acquisition systems that continuously gather data on various parameters, such as temperature, pressure, vibration, avionic buses, really anything on the system. I was doing a little digging and I found out that currently there's an order of magnitude more devices logging data to the internet than people in the world. And it's increasing at an exponential rate. Think about that. That is a lot of monitoring. Think about the ramifications of that. So what is continuous monitoring and how does it work? Well, let's start from the bottom and work our way up. At the bottom, we have the assets we wish to monitor or control. Most industries these days are participating in this. The assets are connected to some kind of device that can acquire information from and or control the asset. This edge device is also the communication pipe to the internet if needed, whether it is by some wireless interface like satellite or cellular, or short-range Wi-Fi or Bluetooth, or even just local logging. This is locally, and then use sneakernet to move the data. Let's call this the data storage cloud regardless. The data is passed to this cloud or a broker that holds the data. An application is written to process and present the data, whether it is to an asset tracking system, a health and usage monitoring system, or even a point of sale system. They are all getting their data from the cloud and not directly from the device. Then the subscriber of the data will display the final results on a display device, whether it's a phone, a PC, or any other kind of GUI. If we talk about moving data over the internet, the basic data packet structure must conform to the Internet Protocol Suite. Two examples of clouds that can hold this data that UEI's hardware supports are MQTT and the VxWorks Helix device cloud connection. So let's quickly review how it really works. So on the left, we have our UEI pack or embedded computer with I/O and avionics interfaces acquiring information. It can pass the data via Wi-Fi, copper or fiber Ethernet, or with a CDMA or a GSM modem, or just log it locally. We publish the data to a broker, a middleman, could be a cloud, perhaps even the MQTT or the Helix cloud. And then your subscriber would use a mobile device, maybe a phone, a laptop, or something else to review and analyze the results. So what's MQTT? Well, MQTT stands for MQ Telemetry Transport. It is a publish and subscribe model, extremely simple and lightweight messaging protocol. It's designed for constrained devices and low bandwidth, high latency, or unreliable networks. The design principles are to minimize network bandwidth and device resource requirement while also attempting to ensure reliability and some degree of assurance of delivery. These principles also turn out to make the protocol ideal for the emerging machine-to-machine or M2M interface. This is where mobile applications are bandwidth limited and battery power are at a premium. This system handles the basic communications, the retries, and the connections. From what I understand, it was invented by IBM for satellite communications to the oil fields. Back in the 90s, bandwidth and connectivity were at a premium. And of course, like all good things, it was co-opted for use on the internet that we use today. So here's a quick application example, a pump monitor. The user would like to monitor the vibration characteristics of this pump. We can embed accelerometers and our hardware to acquire the data, calculate the fast Fourier transforms or FFTs to determine the frequencies and the magnitudes of the vibration. The data can be then passed to the cloud that aggregates, or it can be logged locally and then alarm on a high vibration at a certain frequency. Anyone, anywhere can subscribe to this data. This can remove the need for spot checking with expensive equipment that you may have to purchase or rent to go up to these devices to check them. So let's take a quick snapshot of how this all works. So we have our device, and it is getting the data, it's logging its data, and it's storing it. Other people who want to get this data have no knowledge of where this device is necessarily, and no necessarily time dependencies on it. They just know that they are going to get this data and review it. And there's really no synchronization between them. They just have these data sets that they need to look at. However, once the data is moving, we need to think about some security issues. Even though it is maybe pushed over the internet and TCP/IP in general has security concerns. For instance, remember when there was that denial of service attack with webcams, security cameras, and DVRs? Tens of millions of unique IP addresses involved in this massive botnet that managed to knock out Twitter, Amazon, and other sites for many users, all from webcams and security cameras. We certainly don't want to participate in that. So one way to combat that is something called Internet Protocol Security, or IPsec. It is a network protocol suite that authenticates and encrypts the packets of data sent over a network. IPsec includes protocols for establishing mutual authentication between agents at the beginning of the session and negotiation of cybergraphic keys for use during the session. IPsec can protect data flows between a pair of hosts, between a pair of security gateways, or between a security gateway and a host. Internet Protocol Security uses cryptographic security services to protect communications over IP networks. IPsec supports network-level peer authentication, data origin authentication, data integrity, data confidentiality, and replay protection. Encryption algorithms compliant to FIPS 140.2 can also be used. Really, any kind of cryptographic encryption algorithms can be used over IPsec. So now that we know we've got a secure network here, other attributes of this system are quality of service. So along the way, you can measure quality of service. Is it one message that just goes and you hope it gets there? Is it a message with a handshake that says, I got your message? Or is it a connect, confirm that you're real, get the data, and then confirm that you got it? So there's various methods to do this under the hood. As well as, of course, you need your last will and testament should an asset go down that says, here I am, here's my state, and here's what time it is. So how does this apply to aerospace? Well, at the forefront of this revolution is the world's commercial jet aircraft fleet, with an increasing myriad of sensors to monitor systems and provide real-time offloaded data over a connection that is increasingly becoming an essential aircraft system. Advanced antenna technology will enable even higher bandwidths. Already, any issue of internet capability is increasingly affecting the go or no-go decision for business jets. Here's an example of the future magnitude. Bombardier's C-Series jets carries a Pratt & Whitney geared turbofan, or GTF engine. It's an engine that comes with 5,000 sensors that generate up to 10 gigabytes of data per second. A single twin-engine aircraft with an average of 12 hours flight time can produce 844 terabytes of data. I think back in the early 2010s, like 2014, I think it was estimated that Facebook accumulates around 600 terabytes of data per day. Well, compare this to a flight of 844 terabytes. But there's an order of Bombardier to book over 3,500 of these GTF engines, of course, all potentially downloading zettabytes of data once all their engines are in the field. Pretty soon, the amount of data generated by the aircraft industry, the aerospace industry alone, could surpass the magnitude of the consumer internet. Not only is more data created by industries than the consumer world, it's more valuable, validating the sentiment that not all big data is created equal. Instead, the data created by industrial equipment such as jet engines, gas turbines, and MRI machines has more potential business value on a size-adjusted basis than any other types of big data being generated from the social web, consumer internet, or other sources. Most of the engines today have less than 250 sensors. For someone who has built engine health monitoring solutions on big data platforms and demonstrated the reduction in the processing time from days to minutes, the new engines are a different ballgame. These scales are beyond imagination, and the kind of data storage and computing infrastructure required to handle such data is truly mind-blowing, but we're seeing it now. Questions could be asked around why so much data is needed and what they're going to do with it. The GTF engines use great swaths of data to build artificial intelligence and predict the demands of the engine in order to adjust thrust levels. As a result, GTF engines are demonstrating a reduction of fuel consumption by 10 to 15% alongside impressive performance improvements in engine noise and emissions. Pretty amazing. So if we look at yet another aerospace application, this is on the ground. Auxiliary power units, or APUs, are used when the main engine is not in use. This would be a pretty easy candidate for on-platform test. It never leaves the ground. Adding a piece of hardware to the APU to continuously monitor the status in any error conditions. You can instantaneously know the state of any APU on the property. You can treat it as a Coke machine like back in 1982. Anybody, anywhere can determine the state of that APU. I think we got this. We've got hardware that monitors the APU, sensors, avionic buses, even external conditions if needed. The data can be saved locally, pushed to a server or a cloud, whether it was wired or wirelessly. Using this data, a supervisor can view the status of all the assets, making maintenance and deployment decisions with up-to-date information. So much of what we are discussing is also called health and usage monitoring, or HUMS. HUMS is a sensor-based monitoring system that enables condition-based maintenance by measuring the health and performance of mission-critical components in these aircraft. By continuously monitoring data from all these sensors at numerous points throughout the asset and pinpointing mechanical faults before they become catastrophic failures, HUMS provides actionable information that allows informed maintenance decisions. A proactive approach heads off accidents before they happen, greatly enhancing safety. Data signaling potential problems on one aircraft can be used to comprehensively analyze the entire fleet. Better maintenance planning means less unplanned downtime, faster turnaround, and increased mission readiness to support the warfighter. This, of course, increases your availability. And CBM also substantially cuts maintenance and operating costs in the near term and over the life cycle of the aircraft, and avoids costs of spare usage, dedicated test flights, and asset recapitalization. This definitely reduces costs. So CBM addresses problems and gives solutions all across the entire spectrum from maintenance and safety. Is my equipment ready now? Is it safe to fly? To your strategic planners, what can I do to improve overall fleet availability and cost containment next year? To your flight planner, how many aircraft are prepared for flight today, this week? And of course, the logistics side of things. How many parts do I need next week, next month? What are they? So how does a condition-based maintenance system work? Well, again, we've got onboard data acquisition units that collect analog data from sensors embedded throughout an aircraft's drivetrain and converts it to digital data. The data is downloaded by the ground support crew and can be used to monitor the health of a single aircraft or an entire fleet. Diagnostic algorithms automatically analyze this acquired data, providing a comprehensive indication of aircraft machinery and health. Software and web-based tools communicate the needed repairs and suggest maintenance actions. This is a real working application. So looking at some of the results, CBM complements performance-based logistics, and the United States Department of Defense Preferred Weapon Systems Support and Sustainment Strategy demand this. Another example is Airbus. Almost half of its aircraft have health monitoring systems that interface with the Flight Operations and Maintenance Exchange, or FLOMAX. This can handle 10 times the data as its predecessor. There's a huge need for continuous monitoring, time series data, to ensure proper and accurate predictions. Here is yet another example, a little more down on the ground. BAE has a hybrid drive engine system that powers these 40-foot heavy-duty transit buses. There are fleets of these intercity buses all over the world, including here in Boston. We've got a liquid-cooled inverter, we've got air-cooled generators, we've got a traction motor, and of course, we've got the lead-acid storage battery and the management system that goes along with it. There is a logger that's installed on every single one of these that not only monitors J1939 CAN bus, it monitors the engine, the hybrid propulsion control system, the battery operation optimization subsystem, even the air conditioning unit, the thermokin, of course. And it also looks at the door control system, and it has an optional GPS. Sounds like a pretty souped up Coke machine to me. There is a real-time data viewing system while the bus is in service, so they can keep track of where the bus is, as well as looking at what are the status of all the systems. The hardware on board has a custom program that handles all the data logging, the communications, and control. It's all logged locally. And there is a GSM or CDMA modem that is installed to transmit wirelessly any information that is needed. There are more than 1,000 of these systems throughout the world, and even here in Boston. The fleet operators subscribe to the data set that gets uploaded seamlessly when they go into the bus yard. It's either uploaded over Wi-Fi or over the GSM or CDMA modem. The bus operators can then make real-time maintenance and usage decisions based on this data set. We have heard that is an improved vehicle uptime and reduced maintenance costs of up to 13%. So what does this do? For this hybrid vehicle example, it allows for high-level information, miles, hours, and location, to be transmitted anywhere to anybody. It's got a color-coded health system on there for the health state. It indicates any fault codes, and if there's any active issues that need to be dealt with. It can look at the history of any of that. It can certainly look at battery voltage levels, and then, of course, the prediction system will order parts that are needed so that the field support technicians can go and actually repair the problem. There is a study they did, that BAE did, that proved that all this lowers the cost for these bus fleet operators. Ultimately, these monitoring solutions can lead to additional business for these engine manufacturers, the OEMs, and even the operators. In that bus application, the fleet operators paid to subscribe to the data set. Bombardier has an agreement with Pratt to use their EFAST health monitoring system on the C-Series aircraft. Bombardier can earn even more revenue by using this data on a real-time performance of their engines, so they can adjust the way planes are flown and deal with potential issues before they end up grounding airplanes for larger repairs. Other leading players are also on the same path when it comes to embracing this. The new generation of GE engines started pumping 5 to 10 terabytes of data per day. GE expects to gain up to a 40% improvement in factory efficiencies by the application of big data analytics. Rolls-Royce collects similar amounts of data from 12,000 engines across the globe into its data centers. They really value this continuous data. New analytics have been introduced that use environmental conditions outside the engines as well as the engine parameters, all for the goal of extending life and reducing downtime. While engines are leading the charge and embracing this data analytics, avionics systems are also catching up to this trend quickly. The traditional avionics systems transfer about maximum 12.5 kilobytes per second, whereas the Boeing 787 Dreamliners and A350s are using Ethernet-based next-generation aircraft data networks called ARINC 664 that is 2 orders of magnitude larger, 12.5 megabytes per second. This makes it quicker and easier to transmit the information from avionics systems to the maintenance teams on the ground about current flying conditions, as well as any faults that have occurred during the flight. While avionics vendors have been slow to introduce big data applications, they are increasingly open to these proposals. The monitors are also helping manufacturers manage their pay-by-hour engagement models and long-term maintenance contracts at lower costs. With rapid advancements being made with data analytics, it's a truly exciting time to be working in the aerospace industry. Soon, thousands of sensors will be embedded in each aircraft, allowing data to be streamed down to the ground in real time. And who knows? In time, this could drive the famous black box to simply become a backup device. So here at UEI, we certainly support many of those HUMS and CBM systems, and we are here to certainly answer your questions and help you out. So I'd like to open the floor to any questions that anyone might have.
Now's a great time to ask those questions. We've got a few in from Andy Hamilton here. So the first one he's asking here is, what about the cost of portable test equipment? Is that factored into the efficiency of on-platform test?
Typically, the cost of many of those data acquisition systems are pretty low compared to the cost of the asset, meaning the airplane, the engine, the avionics suite, and it's also very low compared to what that data is worth to make their decisions to keep all of these assets working. You're talking thousands or millions of dollars a day of lost revenue with downed equipment. Okay,
thanks. He's also asking about recent data to do with the benefits of CBM. He says the chart that you showed is a little bit old. Have you got any more recent data, or know of any more recent data?
Certainly. In fact, I was just reading this morning. It's a very valid question. The MRO magazine just put out information on HUMS and CBM for, I believe it's Airbus and Rolls-Royce. So yeah, there is, I think the magazine's probably, a day old now. So yeah, I think they've got information.
Okay, and Andy's final question, and as I was saying earlier, this is kind of a little bit to do what I was thinking about in terms of the amounts of data that these kinds of systems generate. I mean, he's asking with regards to the GTF engine that was putting up to 10 gigabytes of data per second and terabytes per flight. He's saying that we perhaps don't need AI tools to predict when maintenance should occur, and that when sensors provide that much data, it's too much to manage. So do we actually need them to? Perhaps we could just lower the refresh rates and provide to minimum requirements, and then instead of having to sort of wade through lots of data. Is that more of any thoughts around that?
Well, absolutely. I think what a lot of firms are doing is instrumenting getting too much data in the beginning and then paring it down to understand what are the most important data sets to be getting and how much. As in, how fast do they need these time series data?
Okay, so there's kind of it's better to be there's an efficiency there that can be honed as well, I guess. Yeah.
Right, okay. And that's what AI is really good at as well, is analyzing those big data sets.
I mean, are there limits at the moment to the amounts of data? I mean, you're only talking you're only limited by your bandwidth, right, or the kind of system itself?
Absolutely, there are limits to bandwidth.
Okay. Yeah.
And that's also part of, or in parallel with that question, is if we take too much data, what are you going to do with it? How are you going to analyze it? So sometimes they're massively distributed systems with nodes doing analysis right there in situ and only passing summary results out.
Yeah.
Or moving big data sets after the fact that then get analyzed. So it's a combination of both.
Okay. Staying with the theme of amount of data, it's not really a question, but it's a comment here from Dr. Fred Blonigan, who's saying for 500 channels per engine, your data acquisition system is enormous in size. So I don't know how you.
Absolutely, it is. Yeah, it's a massively distributed system, and yes, it would be big, but typically those are very large systems as well.
Okay, great. So there's a question here from Umankav Justice. I apologise for mispronouncing your name. Do you have any test case with fighter aircraft that you know of, or you can perhaps you can link up?
Fighter aircraft. We have experience with helicopters, with Huey helicopters. At UEI, we do not have experience with the data sets that come from fighter aircraft yet.
Yeah, I guess they would be difficult to get hold of as well. I mean, famously, the F-35 is, you know, a flying computer, right?
Yeah, the U.S. military tends to keep their data close. How's that?
Yeah, can imagine. Okay, so there's a question here from someone called Daniel M. Wells regarding aerospace applications of HUMS CBM to reduce scheduled maintenance. What's your experience of the certification challenge around replacing traditional human-centered condition checking with HUMS? So I guess his question is kind of about.
Yeah, so HUMS is used in addition to this. It is meant to supply data so a human-centered condition checking system will be more efficient at choosing what to fix, where to check, what to look at, versus my engine's not running, what do I do? Where do I start? As well as doing predictive maintenance so that you can get to it before there is a catastrophic failure.
Why doesn't everyone use these kind of systems, you know, continuous monitoring systems? Is it a kind of case of there's just not much need in some places? Is it a cost thing?
I think it's a combination of a couple of factors. There are some older industries that haven't embraced it yet because they haven't invested in the infrastructure. Sometimes their assets are aging and are fixed, so they haven't spent a lot of money on the preventive side. We certainly are seeing that many of the new requirements coming out for many new vehicles, many new engines, many new systems have a CBM device attached to them in the beginning as part of the initial test builds even. So it's almost by definition that this is being designed in from the very beginning versus an add-on after it's already in the field.
Sure. Okay, right. I get you. All right. And finally, one other final thought of mine. I'm just wondering. I mean, how these systems? How do they kind of handle false failures if that happens? I mean, can that happen? I mean, how would they handle them?
Absolutely, false failures happen. And one of the things that we ask is, well, can your CBM or HUMS system diagnose itself to ensure it isn't the fault, that it is reading the sensor, reading the bus correctly? Once your system can analyze that and say yes, then you can go back to the data set. And that's really where these big data algorithms and AI come into play to reduce those false failures based on real data.
Okay, thanks. I've just got one other question as well, actually, and that was around it kind of crystal balling a little bit. I mean, I write also a lot about hybrid systems, and I know you had the bus on there, the hybrid bus, which is an application I've seen before as well. With the amount of electric aircraft and battery systems and that are coming in, that are being integrated into aircraft, do you see any, is there any evolution to take place in terms of these kind of condition-based monitoring systems and HUMS systems? What's the kind of development pathway? Are they developed in parallel with these batteries? Are they part of the battery cell systems? Do you have any experience of that?
Yeah, absolutely. So many of these systems are set up to begin with CBM designed in. So, for instance, many of these battery management systems, BMSs, have a communication bus, so to speak, that you would monitor various messages as well as trouble codes. So they diagnose themselves, give you trouble codes. They also send you information, and that information is easily collected and analyzed in a bigger data analytics system for CBM. And so it seems like many of these systems, a lot of that is being designed in from the beginning versus an add-on after it's already out, which is great. It makes our job that much easier.
And just one final thing I wanted to pick you up on that you said, I hope you don't mind, but you said that avionics suppliers have been have been slow to adopt kind of big data solutions in their systems. Is there a particular reason for that? I mean, sorry to pick you up on one particular statement, but it's just interested and piqued my interest.
Yeah, it is interesting, and I haven't figured exactly why yet, because certainly we're asking them if we can help. We've seen a lot of progress in the engine side of things. Maybe the engine failures are more than the avionics failures, so they're concentrating on the big problems first and then work their way down.
Sure.
But these engines nowadays seem to be very reliable, but they also put out a lot of data, which is so valuable. It's super valuable.
I think I'm going to close the Q&A session there. Eric, have you got anything you'd like to add at the end there? I find it quite an interesting chat, really.
I certainly appreciate everybody's time today. Some of you, it's almost the end of your day, and it's right in the middle of my day here in Boston. So thank you so much.